Now this next one gets a little more complicated. If we check out this question, how much energy is needed to change 150 grams of solid ice? And here this is important. Looking at solid ice, from 0 degrees Celsius to 50 degrees Celsius. Now that tells you one thing. First, if it's solid ice and it's going to 50 degrees Celsius, we know that water melts at 0 degrees. And we know at 50 degrees it's liquid water. So what this is essentially telling us that the heating curve, we're starting with solid water, H2O, solid, and we're turning it into H2O, liquid. That is a phase change. So there's going to be a heat associated with adding thermal energy to the sample of ice, and also heat associated with changing the phase of the ice from solid ice to liquid water. And that's going to be expressed in the heating curve right here. Now if we look back at our slides, we have a value for a phase change, and that's Q equals the mass of the substance times the enthalpy of fusion, which is how much heat is required to melt ice, essentially. Now if you look at the heating curve here, this is how we start every calorimetry problem that involves both a phase change and an addition of thermal energy. You have to know where it starts and what phases it goes through, because each portion of the line represents a different Q value, and you have to solve for each Q value over the heating process to determine exactly how much heat is added. So when I start these problems, I'm going to draw my heating curve first. And I always start by just drawing a line right here, indicating that we're going from solid ice at this side to liquid ice at the other end. So at this end we have solid ice, at this end we have liquid ice, and then it's going to increase to 50 degrees Celsius. So we have two Q values here. We have Q1 and we have Q2. Q1 is going to be a phase change, which is going to be represented by Q1 equals M times delta H. We have Q2, which is just an addition of thermal energy, and that's going to be M times the specific heat of liquid water. In this case, this is H2O liquid, not solid, and that's very, you have to be very important, very careful about that. And then times the change in temperature. So if I substitute in the values here, we're starting with the same amount of ice, 150 grams. So we can say this is going to be 150 grams times the change, the delta H fusion, which happens to be 6.0 kilojoules per mole. Kilojoules per mole. Now, in this case, when we're looking at moles, 6.0 moles, we have to convert the grams of water right here into moles first. We know that solid ice, H2O, has a molar mass of about 18, right? So we can say that it's 150 grams times 1 mole for every 18 grams, and you're going to get a value of, all right, so 150 times 18 gives you 2,700, oh, that's wrong.
No, divided by.
150 divided by 18, thank you, gives you 8.3 moles. 8.33 moles. So it's going to be 8.33 moles, which are going to cross out. 8.33 times 6 is going to give you a value of 50. So in this case, Q is equal to 50 kilojoules. 50 kilo. You know what? This is bothering me. Let me fix this. $50 kilojoules. Beautiful. And then down here, we have the mass, which is still the same mass, 150 grams, times the specific heat, which is 4.184 joules per gram Celsius, times the change in temperature, which is going from 0 to 50. So we can say 50 degrees Celsius. Now we can cross out the grams, cross out the Celsius, and we get 50 times 4.184 times 150 is going to give us a total of 31,380 joules, or 31.38 kilojoules. So 31.38 plus 50 is going to total 81.38 kilojoules of energy total. And that is your answer.
Why did you add 50?
Because Q1, this is Q1 plus Q2, is going to be this guy plus this guy. All right, hope that helps.